Hi, everybody. Today I'm going to talk about reward-aware proto-representations in reinforcement learning. So this sort of representation is sort of like a new kind of representation. But before diving into the details of this reward-aware representation, we're going to first... Oh, camera. Yeah. So before diving into this new form of representation, we're going to first start with an older form, the successor representation, and explain why it's not sufficient in some cases. So let's start with the successor representation, which captures the expected discounted future visits to other states. That's the standard equation for the definition, but it might be easier to explain this with a simple example. So in this example, we have 5 states. Every state can be represented by a one-hot factor. And let's say we start in this particular state, the one-hot factor with a 1 in the first entry, indicating the first state. And if the agents start here and follow the policy, there's different probabilities of reaching different next states, and so on. So we can sort of enumerate all the future probabilities, future outcomes, possibilities. And what the successor representation does is that this factor summarizes all of these future visitations. So all of that future information is going to be summarized in this one factor, where each entry in this factor is going to represent the expected future visits to one state in the environment. So there's total of 5 states in this simple example. That's why the factor is 5-dimensional. So more generally, the dimension of this factor is equal to the number of states. So in this example, we have 5 states, each corresponding to a 5-dimensional factor. We can sort of stack them together, and this forms the successor representation matrix, denoted as psi pi. We have a superscript pi here because this successor representation is dependent on the policy. If the policy changes, the future outcome changes, so the values of this matrix will change. Now, it's a good time to look at some visualization of the successor representation. Here we compute it with respect to the uniform random policy. In the environment shown on the left, which is basically empty, the agent is free to move up, down, left, right. And on the right, we show the successor representation, so the factor for a particular state. And it is this middle state. And we can see that there are different colors, the color red, different shades. The deeper the color, it means the higher the value. And this successor representation has the highest value in the starting state. This makes sense because imagine an agent starting in a position and it's just walking randomly, doing a uniform random walk. It's going to visit its original position the most. And as the distance from the starting state increases, the probability of visiting those further away states will be smaller. So this is why the value is highest in the middle in the starting state. And as you go further and further away, the value decreases. And since this is a square matrix, we can take the eigendecomposition and get eigenvectors. So if we do that, we have a bunch of eigenvectors. We can order them by the eigenvalue and in the descending order. So here are some examples of eigenvectors that you can get in the environment that we just showed. And we can see here that sort of when the index is increasing, meaning that the eigenvalue is decreasing, we have sort of a higher frequency in the eigenvector. And generally, when you have a larger eigenvalue, it is smoother. And it very nicely captures structure of the environment. So in the environment on the left, the agent is starting in the blue state, and it wants to go to the green state. And we can compute the eigenvector, see the eigendecomposition, get the top eigenvector. And that is going to show basically that vector on the right, that visualization on the right, which is the highest in the goal state and a smaller value as the distance from the goal state decreases. So, and it is also aware of the structures in the state space, for example, the walls, all those things. So it is the eigenvector of the successor representation has nice properties, which allows it to be applied in many applications. One of such applications is reward shaping. But in reward shaping, the goal is usually for the agent to reach the task is usually for the agent to reach a goal, but the environment reward may be too sparse or not very informative, and it's generally not quite enough for the agent to learn to reach the goal. So for example, in this environment, the reward functions is -1 everywhere, except for 0 for reaching the goal state. Now, if the agent is facing this reward signal, it is kind of hard for it to learn because it sees a -1 reward everywhere, almost everywhere. And the goal of reward shaping is to construct an extra reward signal that is usually denser that will help the agent reach the goal. Yeah. How do you compute this derivation? Oh, we can learn them using temporal difference learning. Oh, yeah. So the question was in standard RL, how do you learn this successor representation? And if you can learn this successor representation using temporal difference learning, why couldn't you just learn the policy, the optimal policy at the same time? Yeah, so in this particular setting of reward shaping, people usually assume that you have prior access to this eigenvector of the successor representation. But there are cases, for example, in other scenarios where we can do both of them at the same time. So we learn the eigenvector or the successor representation simultaneously as we're learning. So it is possible. But just for this case that we're considering, we just assume that we're given the eigenvector in advance. And then we're going to use it to encourage learning. Yeah. So yeah, on the right, we show the top eigenvector and sort of the 3D landscape. And this is actually a pretty good reward signal because if we look at the form of the reward, it is doing a difference between the eigenvector entry of the next state and the eigenvector entry of the current state. And we can see that the value is sort of increasing as you get closer and closer to the goal. So what will happen in practice when you apply this for reward shaping is that it is going to give the agent a bonus when it gets closer to the goal, and gives the agent a penalty when it gets farther away from the goal. And this is a denser reward signal than the original environment reward, so it can speed up learning. Yes. The goal is the green thing over there. Bottom right. This is actually, this room. And this is actually this room. Yeah. Sort of like rotation. Yeah. So applying this for reward shaping, yeah. Seems like this successor representation going to be really big at the start state, or whichever state you're computing the representation for, and then get smaller as you go away from it. Right? Yeah. So is this a successor representation for the goal state that is big at the goal is small? Yeah, it has the property that it's kind of highest at the goal. No. That is the so let me repeat the question. The question is this thing shown on the right, is this the successor representation computed at the goal state? The answer is no. This is actually the top eigenvector of the successor representation. It is not the same thing. When you compute the eigenvector of a matrix, that matrix is like the probability matrix, right? The probability of these. Right? So how does the goal enter into that time? Yeah. So the question is, how is the eigenvector aware of the goal? How in the computation, how does the goal information enter? So when you're computing the closed form successor representation, you're using the equation I minus gamma p pi. Yeah. And then in p pi, there are different ways to formulate the terminal state. You can treat it as an absorbing state. So it would have a 1 in the diagonal entry. corresponding to the terminal state. But you can also treat it as a state that transitions to an absorbing state. And if we use the latter formulation, this gives this eigenvector. Okay. And what if we want to do this whole thing again, but in a different environment? So previously, the environment is just the state and the goal, a start state and the goal. If we're doing it in an environment where we have a low reward region that the agent should avoid, we actually get the exact same thing because the SR doesn't take reward into consideration. If you remember a few minutes ago, when we're enumerating all the future probabilities and then including all of that information in a single factor, the reward doesn't show anywhere. So the successor representation is fundamentally reward agnostic. This is why we get the same top eigenfactor, even though we introduced the low reward region. And if we look at the direction that would give the agent the maximum reward bonus for this extra reward signal, the direction is actually this, which goes through the bottom left room and through the low reward region. So when we try to use this eigenfactor for reward shaping, we're sort of encouraging the agent to do something that is suboptimal because of the low reward. So this can be a problem. So here's a brief summary. The successor representation captures future state visitation. Its eigenfactor captures the structure of the state space, but it is reward agnostic and can be problematic in environments where reward awareness is important. Are there any questions at this point? Okay. So this problem doesn't only happen with the successor representation, but also with its variants, such as first occupancy representation and lambda representation. We call all of these proto-representations, proto meaning primitive or original. Since these representations, they're defined directly using the transition and dynamics of the environment. So they're sort of primitive to the definition of the MDP. So we call them proto-representations. But the problem, as I just said, is that they're reward agnostic. And the solution, of course, is to use something that is reward aware. And the particular candidate that we studied in our work is the default representation, which captures both the transition dynamics and the reward function. And now I'm going to explain how the DR, or the default representation, is able to do that. So recall that we can stack all the successor representation factors together to get a matrix. We can sort of do the same for the default representation, and they have the same dimension. Now we're going to focus on one particular entry in this matrix. On the second row and the fourth column, that particular entry that relates the second state and the fourth state. And we're going to show how these two representations capture different information for every single entry. So now we have two states, S2 and S4. And we can enumerate all the trajectories going from S2 to S4. And for simplicity, let's assume that there's only 3 trajectories. So those are the 3 trajectories going from S2 to S4. And there are different statistics of this trajectory. For example, we can have the probability of following this trajectory. So here we are assuming that both representations are computed with respect to the uniform random policy. So p tau here would be the probability of this trajectory under the uniform random policy and the transition dynamics. We can also look at the sum of rewards that you get along the trajectory. That is the R of tau, the undiscounted return of that trajectory. Finally, we can look at the length of a trajectory. So those are the 3 things that we can look at. And both the successor representation and the default representation, they take into account the probability of the transitions. So they both look at P of tau. But from now on, things are going to be different. The successor representation is going to look at the length of the trajectory, while the default representation is going to look at the reward that you obtain along the trajectories. And that particular entry is computed in this way. And we can view it as a weighted sum of the statistics of the trajectories that are enumerated. And the weights here is the P of tau. So you can think of them as the weights in the weighted sum. And the thing that we're summing over is the thing in red, which are different for the successor representation and the default representation. For the successor representation, it captures the number of transitions it takes to get from one state to another. But for the default representation, it captures the reward along the way when you travel from S2 to S4. And as, for example, for the successor representation, gamma here is a discount factor. There's some number that's between 0 and 1. And if the sort of the average number of transitions it takes to get from S2 to S4 is large, then we're applying a lot of discount. Then the corresponding entry in the successor representation matrix is going to be small. So the successor representation matrix captures the distance between states in terms of the average number of transitions it takes to travel between them. On the other hand, the reward, it is the sum of the rewards that you get along the trajectory. If for the trajectories going from S2 to S4, the sum of rewards on average is kind of high, then this is Z of S2 and S4 is going to be high. So this default representation matrix captures distance in terms of the sort of the average reward that you would get when you travel between different states. So that's why the default representation is reward aware, while the successor representation cannot do that. And every entry would capture those sort of information. And here's a visualization of the successor representation and the default representation of the start state, which is the blue state in this environment. As we can see, similar to the earlier case, the successor representation is just the largest at the starting state and just sort of decreases as you get further and further away. While the default representation is kind of doing the same. However, the critical difference is that in the low reward region, there's a sudden dip in the value of the default representation. Yes. Yeah, so P of tau, so sorry, the question is explain more about P of tau. So yeah, so imagine you have a trajectory, state, action, next action, all the way to a final state. P of tau here is going to be the probability of taking the first action times the probability of transitioning from the state action pair to the next state, and just the multiplication of all these terms. What? Yeah, we're assuming that both of these are computed with respect to a uniform random policy. Sorry, can you repeat the question? Yes, exactly. Yeah. Yeah. Question?
What would the default representation look like if the reward is not 0?
Reward is not 0?
Rewards are all 0.
Oh. Okay, so the question is, what would the default representation look like when the reward is all 0? And one assumption that I forgot to mention is that we assume the reward is negative at every single state. But I guess your question is also valid, is what if all the states have the same reward? In that case, the default representation would sort of look similar to the successor representation. And is it actually possible to prove that they have the same eigenvectors? Yeah, if you have a constant reward at every time step, the sum of rewards, it's sort of like the distance. So in the case of a constant reward, it would just capture similar information as the successor representation. Oh, because the default representation doesn't make use of the discount factor. Yeah. Action?
You said that it will be equal to FR, but there's no discounting, right? The gamma is not there. So the private.
Yeah, so the question is, when we have a constant reward function, why would the default representation be able to capture similar information as the successor representation? So this is basically the sum of rewards along the R of tau is the sum of rewards along a trajectory. If you have a constant reward, this basically counts the number of steps in the trajectory. And if we break the sum, exponential of a sum is just the multiplication of the exponential of the individual terms. So each individual term, since we assume that the reward function is negative, exponential of a negative number is a number between 0 and 1, and that sort of serves as the gamma here. Return of the trajectory, yes. Yeah, you can think of it that way, but in the case of constant reward function, it's sort of similar to a discount. But in the case of a richer reward function, it's doing something more. Any other questions? So we saw that the representations, they are different because the DR is reward aware. And now we can also look at their top eigenvectors. As before, the successor representation just has the highest value in the goal and just diffuses across the state space. The default representation does sort of the same. However, in a place where there's a low reward region, there's a sudden dip in the values, like a valley. So that is why it is reward aware. So we can, because of this property, we can also use it for reward shaping and to solve our previous problem that the successor representation could encourage suboptimal behavior because it is not reward aware. So if we look at this top eigenvector or look at the landscape on the right, if we look at the direction that would give the agent the most reward shaping bonus, for the successor representation, it's going to be the direction that goes through the bottom left room, same as before. But for the default representation, it would be another path that goes through the top right room, avoiding the low reward region. So now we apply this for reward shaping to see if it actually helps with performance. So we perform experiments in these 4 environments. And a reminder that that is our extra reward signal that we're providing to the agent. And here we show the performance of the reward shaping in the 4 environments. And here the x-axis is the number of steps the agent has interacted with the environment, while the y-axis is the return that the agent gets. And up is good because we want more returns. Purple shows the performance of the default representation. Blue is the successor representation. Green is the baseline that we can ignore. And red is no reward shaping. And there are 2 observations that can be made here. First, both the default representation and successor representation is better than no reward shaping. This is because they provide a denser reward signal than the original environment reward function. So they help improve the learning speed of the agent. The second observation is that the default representation, by being reward aware, is able to correctly encourage the agent to follow the optimal path. That's why it's able to perform better than the successor representation. Any questions here? Oh, yeah.
Why the baseline is so helpful for forwards and reverse?
The baseline is sort of like a prior work, also based on the successor representation. Yeah. Yeah. So if there are no further questions, I'm going to proceed to the next part of the talk, which is applying the successor representation and the default representation for option discovery. So we first have to define what is an option. I think of it as an abstraction of actions. So in an environment, you have primitive actions. For example, go up, down, left, right in the environments that we've seen so far. And the option can be thought of as a higher level abstraction of those actions. The key part is an option policy, which tells the agent which actions to take when the agent is following the option. And the other 2 are just where to start the option and where to end the option. The initiation set is just a set of states where you can start the option. And the termination function tells you the probability of terminating the option at every single state. So just the option policy and where to start and where to end. An eigenoption is a specific class of options that are derived from the eigenvector of some representation. So here we have the eigenvector of the successor representation, and we can use this to compute an eigenoption, and I'm now going to show you how. So suppose the agent is transitioning from S to S prime. The eigenvector can be used to compute this term, which is the difference in the eigenvector entry of S prime and eigenvector entry of S. If we treat this as our reward signal, we can use algorithms such as Q-learning to maximize this reward signal, and that would give us a policy, and we call that the option policy. That will be the policy of the option. And intuitively, we can think of it as climbing the eigenvector. So we're going from a low state and a low value state and trying to end in a high value state. This is intuitively what learning the option policy is trying to do. And as for termination and initiation, it's very simple. Since we're trying to climb this eigenvector, we just stop when we've reached the top. So that would be the termination state, where we terminate with probability 1, because that is the highest point in the eigenvector. And for initiation, it's just every other state. If we haven't reached the top, we allow the agent to take the option. And yeah. So in this example, we assume that we have access to closed form eigenvector. But in real problems, when we're trying to solve problems, the agent has to learn from scratch. And we don't have access to this nice exact ground truth eigenvector. And in those cases, we rely on the framework of representation-driven option discovery, usually referred to as the Rod cycle. Rod cycle begins with collecting samples, and then the samples are used to learn the successor representation, the eigenvector of which is used to learn the eigenoption, which is then used to further collect samples. The nice thing about this Rod cycle is that the eigenoption takes agent to underexplored area of the state space. So suppose the agent is interacting with the environment for a while, and there are more visited states and there are less visited states. What the eigenoption is going to do is to take the agent to the areas of the state space that is less visited. So the agent can continue exploring there and to collect more informative samples for improving the representation. So this is sort of like a virtuous cycle where you continually improve the representation that you're learning and using the newly computed eigenoptions to further help you explore the state space that needs to be explored. Now, let's give you a practical example of the Rod cycle. Here, we're using the successor representation for the Rod cycle. On the left, we have the cumulative state visitation of the agent. So for the iterations of the Rod cycle that we've run, what is the cumulative visitations to every state in the environment? In the middle, we have the eigenvector. You can see that it sort of correlates with the state visitation. It's sort of lower in places where the agent has visited more, and higher value, deeper color, in places where the states are visited less. And if we look at the eigenoption and try to draw from try to visualize the direction from the start state, we can sort of look at what the option, where the option is taking us. So the initial state here is the top left state at the very top left corner. If we draw an arrow from there, we can see that the eigenoption, as expected, is taking us to an area of the state space that is less explored. So this is the successor representation, like a snapshot of the Rod cycle. And now we're going to visualize the full cycle. We're going to use the environment on the top right. The agent starts in the blue and tries to go to the green. And there's a low reward region. And one thing to notice here is that when the agent is doing the Rod cycle and trying to explore the different states, since it is not reward aware, the agent is actually going to visit the low reward state pretty often. So you can see as the iteration continues, the agent sort of taking this path a lot because it wants to visit these less visited states here. but the low reward region is here, so it's passing through the low reward region a lot. So this is a problem of using the successor representation with a rod cycle to explore the environment, which is that it is not reward aware, and it passes through low reward region. If you have some applications where you want to care about the rewards that you accumulate during the course of exploration, then using the successor representation could cause the agent to accumulate a lot of low rewards, which is not desirable. We can instead replace everything where the SR was plugged in with the default representation. So here we're just going to visualize the rod cycle when we use the default representation instead of the successor representation. And as we can see here, it is able to sort of recognize the low reward region. It chooses to go left instead of the bottom, straight through the low reward region. So that is the property of the default representation in the rod cycle. If we take a particular snapshot of the rod cycle, as I said, here are the values on the top 3 rows in this particular room. It's clearly higher than the value here because the low reward region starts here. So the eigenvector is able to accurately detect the position of low reward regions. And if we look at the associated eigenoption, the eigenoption tells the agent to go back if it's reached this low reward region. This is why the default representation is useful in this case. And if we look at the cumulative state visitation counts at the end of the rod cycle for the successor representation and the default representation, you can see that for the successor representation, it passes through this area, which is where the low reward region is located. But on the other hand, it still passes through, I think, occasionally, but the number of times the agent passes through the low reward region is much lower compared to the successor representation. And in order to examine this, whether this is true or whether this generalizes, we run a larger scale experiment in the 4 environments shown before. So here what we do is that the rod cycle has different parameters, hyperparameters. Each hyperparameter could have different values. We just enumerate all possible combinations of the hyperparameters. And then for each hyperparameter, we run the rod cycle for 10 seats and average their performance. And then we visualize the performance of all the different hyperparameter configurations for the different methods. Now, the x-axis here shows the average state visitation percentage, which is computed as imagine that the agent is interacting with the environment for many, many time steps. At every time step, we know how many percent of all the states the agent has already visited. If we average that number across all the time steps, that would give us the value on the x-axis, and that sort of captures how fast the agent visits every single state in the environment. And on the y-axis, we have the reward that is averaged over every single time step. That tells us how reward avoidant the agent is. And then these plots, up, right. So the top right corner is better. This is good because if you're up, you avoid low reward better. Oh, avoid low reward, not avoid reward, sorry, for the typo. But if you're to the right, you visit states faster. And the green shows the performance of the rod cycle using the default representation, while the red shows the performance of the rod cycle using the successor representation. And as we can see here, across different hyperparameter settings, it is a general trend that the rod cycle using the default representation achieves higher reward than the rod cycle using the successor representation. However, if we try to visualize the point, the hyperparameter setting that leads to the highest state visitation, you can see that the default representation in general achieves a slightly lower state visitation. So it doesn't visit all the states as quickly as the successor representation. And that is just a necessary sacrifice, I think, if you want to avoid low rewards. Because in our previous example, as we saw, we want to avoid that low reward region in this third environment right here. It needs to take a longer path in order to visit the states, for example, in the bottom row of that environment. So in order to avoid low reward region, it sometimes has to take detours, which explains why using the rod cycle and the default representation could visit the states lower than using the rod cycle with the successor representation.